Welcome to the lecture series on vitamins and nutrition. Today we are going to look at a very important vitamin. This particular vitamin, what we call it as vitamin B12, is a very important vitamin in terms of its structure and its application and its metabolic role. So today we are going to look at different aspects of this vitamin B12. We are going to look at the origin of this vitamin, the sources of this vitamin, and the structural features of this vitamin, and a bit about its absorption and the way how this vitamin enters our system. So this particular vitamin, as we call it, vitamin B12, which is popularly known as cyanocobalamin. So vitamin B12 is the common name being used by many people, but actually if you consider this particular vitamin, this vitamin is a complex vitamin in terms of it's available in 4 different forms. In fact, if you look into the structure, this vitamin is a very interesting structure. See, the structure is too complex. In fact, this vitamin can be called as the largest vitamin and structurally very complex vitamin. In fact, if you look into the historic background of this particular vitamin, especially the structural elucidation, had been a tough journey for scientists. Probably we will separately go for a detailed session on the historic background of vitamin, but before we go into it, I thought I'll explain about this vitamin, its metabolic role. So for this discussion we will be looking into its origin and metabolic function in detail before we venture into the way how this particular vitamin was elucidated. In fact, for you to get yourself excited about this particular vitamin, be aware almost like 5 Nobel laureates had been associated with this particular vitamin. The discovery, the pathway, the way this vitamin has influenced the scientific community is really enormous. Look at this structure. So you see there, this particular vitamin has lots of pyrrole ring, saturated pyrrole ring, and you have this corrin ring structure. Okay, so in fact it looks like a kind of a complex. So the way how this cobalt metal is coordinated with this complex structure is in itself is a beauty to look at, and for a very long period of time it has been a challenging task. Say for way back 10 years people had been struggling to solve the structures. 2 different groups in different aspects of research had been involved exclusively to solve the structure. So you see it has such a tremendous impact on scientific community, and it's worth it because this particular vitamin has actually been useful in various metabolic processes, and its combination in line with folic acid, iron had been the stable source for all sorts of anemias. So you do have a separate category of anemia, what we call it as the pernicious anemia, which results because of vitamin B12 deficiency. And since the absorption of vitamin B12 in itself is a very complex process, or rather you say involves lots of steps and other accessory factors before the vitamin B12 could be made available for systemic circulation. So the journey and discussion for vitamin B12 is really worth our interest. So you look here, as the structure says, this is the structure of cyanocobalamin. But you see here this R group, the cyano group attached over here, it can be replaced by an hydroxy cyanocobalamin. Then you can have adenosyl cyanocobalamin. Then you can have a methyl group as methyl cobalamin. So if you look into the structure you will understand it better. So look here, you do have other names, synonyms for this particular vitamin as we call it. It's also called cyanocobalamin, anti-pernicious anemia factor. It's also called the extrinsic factor of Castle. So there is in this way what we call it as an intrinsic factor. So this being the extrinsic factor has to bind with the intrinsic factor. We are going to see shortly how this works. So you see there, if you have to have a quick look of this particular vitamin, it's a water soluble vitamin. So it comes under that category I have told you earlier. And as a water soluble vitamin, it can be quickly lost, but you do have good resource, or I would say, the storage mechanism for vitamin B12. So we don't show deficiency instantly as with other water soluble vitamins. So you do have a reserve, but if the reserve is depleted and if not properly taken except for an intravenous route, the oral route of vitamin B12 involves lots of steps. So you see that as a vitamin, it is extremely essential for CNS, central nervous system function, especially myelin degenerative conditions have been associated with vitamin B12, and especially people who have an underlying disease that can predispose them to nephropathy, I would say degenerative conditions connected with nerves. There are some diseases, for example, diabetes is one such disease where people who suffer from diabetes, especially people who have uncontrolled diabetes, have a tendency for degenerative conditions of the neuron. And this is accompanied by vitamin B12 deficiency, then the progression of degeneration is quite rapid. So that's why this category of people who suffer from diabetes, especially uncontrolled diabetes, have to take supplements of vitamin B12 to delay the process or to really halt the process. In fact, there is one more clue you need to remember. One of the common diabetic drugs, metformin, which is used for therapy in diabetes, also have an inherent tendency to cause vitamin B12 deficiency. So you see, it all adds up to the condition. So people with diabetes already have this problem of nerve degeneration, and they might need an additional supplement of vitamin B12. And moreover, they also take a particular drug that can predispose them to vitamin B12 deficiency. So it goes very complex. So that's why in general, for the well-being of diabetes, as a dietary supplement, vitamin B12 is always recommended on a oral tablet based therapy. And for people who already show degenerative conditions, it's recommended to take vitamin B12 through intramuscular route in a periodic level and do a very constant monitoring of vitamin B12 levels in their circulation. And as I've told you, this particular vitamin also makes it very interesting because it's produced by bacteria and archaea bacteria. So you see, it's not synthesized by animals, plants or fungi. So even in animals, we are only dependent on dietary source. We do not biosynthesize vitamin B12. So that makes vitamin B12 all the more precious. So you don't make it, and you are completely dependent on bacteria for producing it, and especially gastrointestinal bacteria can produce it, but they may not completely supplement the needs what we have for this particular vitamin. And moreover, we also have this problem of dietary dependence on vitamin B12. Suppose if we do not have a sufficient intake of vitamin B12, we would end up in a permanent deficiency. So vitamin B12 deficiency can happen and can aggravate underlying pathology in a very rapid manner. So that's why vitamin B12 supplement in itself has become a huge industry, especially vitamin supplement industry. And in addition to that, in nutritional sciences, it's been one of the primary vitamins along with fat soluble vitamins to be fortified in majority of the food, because probably processing food we will lose this particular vitamin like any other water soluble vitamin. So the food company that needs to process the food, who sell large scale production, who do large scale production of macronutrients, try to fortify their products with vitamin B12. So you see there, as a dietary source, as I've told you, since they are synthesized only by microorganisms, and especially if you look at the ruminants, they obtain it from the foregut. Okay, so we dependent on dietary source for this particular vitamin. So even in diet, if you happen to be a vegetarian, it becomes all the more difficult, because for people with a non-vegetarian diet, okay, who consume meat products regularly, may not show deficiency for vitamin B12, because as you see there, meat, fish and dairy products are very good source. So for people who have a dietary choice of who are vegetarians need to take sufficient dairy products to really have a daily input of vitamin B12. So you do have vegetables, fruits and other foods and non-animal origin are free from cyanogobal unless they are contaminated by bacteria. So it means what? Inherently these foods don't have, but probably if they have a kind of symbiotic relationship with the bacteria, or if they themselves have been a source for bacteria to grow, in such cases, yes, they can, but that's not a stable source. People are strict vegetarians who are very particular about the diet of taking only vegetables are at risk of developing vitamin B12 deficiency. And as I have told you now, if they already have this problem of diabetes, then it makes even more difficult. So you see that, as you see over here, you find a lot of seafoods, okay, fish and lot of crustaceans over here. Then you have egg as a source, then you have meat products, red meat, all this being excellent source for vitamin B12. So if you look into the dietary requirement of vitamin B12, especially for a Western society, they are prone to take a lot of animal products. So they could take an intake of 5 to 30 microgram of cyanogobalamin daily. So an adult daily loses like say 1 to 3 micrograms of cyanogobalamin in the normal excretory products. So you see the body stores would be like 0.1%, and you see that the body does not have ability to degrade cyanogobalamin. So the daily requirements in this case would average somewhere around 2.4 to 2.5. So you could have a range of around 1 to 3 microgram depending on the activity or the metabolic requirement of an individual. So in average, you see people might need around 2.5 micrograms of vitamin B12, cyanogobalamin every day. The body stores are probably in the range of 2 to 3 mg. So maybe you could have sufficient storage, okay, that could last for years as I would say. But once the supplies are lost, completely lost, then until it's been replenished through a dietary source, then people will not be able to get back this vitamin for a normal metabolic function. So this is one good news in the sense we do have sufficient storage for at least a period of 3 years, and the person could really survive without this particular vitamin. But that's why I said for people with a dietary deficiency of a strict vegetarian diet would end up having a problem of this particular vitamin deficiency accumulated over a period of time. So it's mostly a kind of accumulated deficiency they might suffer from. And as I've told you in the beginning, certain diseases have a natural propensity to crave for more vitamin B12. And again for geriatric population, as you said, who might have degenerative conditions, even people who suffer from Alzheimer's and other degenerative nerve diseases might need additional sources of vitamin B12 for myelin synthesis and maintenance. So if you look at the structure of vitamin B12, so let's discuss on the structure. So you see over there, you have methyl group in this place for methyl cyanogobalamin, and you will have a cyano group for a cyanogobalamin, and you also have a 5-deoxy adenosyl cyanogobalamin. Okay, so you also have a dimethyl benzimetazole in the structure. So this one is what we call it like the Corin ring. Okay, so this is the Corin ring. Fine. So the 6th position occupied by either a deoxy adenosine group, a methyl group or a cyano group. So generally in the commercially available vitamin, we always find cyano group being very predominant. That's one of the reasons this particular vitamin by default is referred as cyanogobalamin by many people. But you do have other types of cyanocobalamin as well. So the cobalamin analogues to heme, okay, in its structure having as its base a tetrapyrrole ring. So this is the structure. So this is the tetrapyrrole ring. So this is the pyrrole ring as you see over there, the tetrapyrrole ring. So this makes the structure very complex. It's a coordinate complex. Okay, so instead of iron as a metal cofactor for heme, so you see there cobalt is in the coordination state of 6. Okay, so if you recollect the basics in chemistry, a coordinate complex is one type of compound which results from a very different bond. You have covalent bond, you have ionic bond, but coordinate bond is little different. So coordinate bond results especially when two atoms of an element would interact in such a way, if one would give an electron and the other one would receive it, you call it ionic bond. And in case with covalent, mutually there would be donation and sharing. And in case with coordinate bond, the electrons would be donated by one group of the compound and the other group, the element or the atom of the element, would share it, so that both would mutually share. So in this case, one would donate and both would mutually share. In case with covalent bond, both would mutually donate and both would mutually share. So all the chelate compounds, as we call it, the complexes, fall under the category of coordinate complexes. So in this case, if you look at hemoglobin, hemoglobin is also a coordinate complex. So heme is one particular coordinate complex where iron would be the ligand. Okay, so it's rich in electrons and you find there a coordinate complex. And in this case, if you look at this structure, it's quite interesting. So you have a cyano group with coordinate complexation with the pyrrole ring assembly. So you see there the benzimidazole group nitrogen is also coordinated to an axial position. So you see that the benzimidazole also providing an axial coordination. So nitrogen in this case would offer the lone pair of electrons, okay, and would accommodate. So here you have a cobalt metal ion and you find that nitrogen has a lone pair of electrons to donate, so it acts like a ligand, and there are empty d shells in the covalent in the cobalt atom, so through which both are able to share the electron pair. So you see that the 4 equatorial positions coordinated by the nitrogens of the 4 pyrrole groups, as you see there. This is the interesting feature. So the pyrrole group offers the lone pair of electrons through its nitrogen, and can you see there all are contributing to this. So this structure gives you an indication of different derivatives of cyanocobalamin. So the R group could be cyano group, it could be hydroxy group. So in that case you call it as hydroxycobalamin. It can be a methyl group, so you say methyl cobalamin, or you can have a adeno group, as you call it as adenosyl cobalamin, which is also the coenzyme B12. So you see there how different compounds can actually end up donating a pair of electrons, okay, or rather forming the coordinate complex. So you see there the vitamin B12, it exists in different chemical forms, as I have told you. The main feature of this structure is the Corrin ring. So in nature, the vitamin is mostly found as a 2-deoxy adenosyl form, which is located in the mitochondria. So that's the natural form. So generally if you could skim through, or if you try to evaluate vitamin D12 in a living system inside the cell, you find the 2-deoxy adenosyl form. So this is the form, what you call it as 2-deoxy adenosyl. So if you replace this R group by this ado, okay, so you get adenosyl cobalamin. So adenosyl cobalamin or coenzyme B12 as it is known is the one which actually is present in the natural form inside the mitochondria. So you see there the other natural form which is in very close association or in the function would be methylcobalamin. Okay, so in the human plasma you find methylcobalamin to be very common, and also in the cell cytoplasm. Okay, so you do have little bit, if you look into the prevalence of this particular vitamin, you have little amounts of hydroxycobalamin. If you look into the structure, you will understand. So you see there the R group can be now hydroxy group as well. So the moment you have an hydroxy group, okay, so you call this particular vitamin as hydroxycobalamin. So hydroxycobalamin generally occurs in a very tiny quantity compared to the methyl or adenosylcobalamin, okay, and they are minor amounts which are similar to the function, and in you say comparison wise it's like methyl and adenosylcobalamin, but they get rapidly converted to hydroxycobalamin after you expose them to light. So most of the vitamin B12, if you see the commercial preparations as well, generally have amber colored bottle for the packaging and sale of cobalamin. It's a dark colored vitamin, okay, it has a very characteristic color. So you have a characteristic red color, and it's being generally sold in a vial which is brown in color. So you see there, as far as the absorption is concerned, so we are going to look at the absorption of vitamin B12. So vitamin B12 absorption is very important to note, because you do have what we call it as passive absorption and active absorption. Okay, so passive absorption, you see that's basically concentration gradient dependent. So you have an higher concentration of vitamin B12, it goes to a region of lower concentration by passive absorption. Okay, so you could expect that in the buccal cavity, in the duodenal, in the sense the small intestine, and the ileal mucosa, it's rapid but extremely inefficient. So like you see, less than 1% of an oral dose being absorbed by this process. So passive absorption is possible, and in that case you are going to consider the concentration based movement of vitamin B12, and less than 1% is being taken up in oral route through this mode of absorption. So the normal physiologic absorption is mostly active. So what is active? It's concentration independent. Even though you might have a reserve of vitamin B12 in circulation inside your body, if you are going to strictly view on the basis of passive absorption, the concentration at the time of absorption would be higher and might move through the barrier membranes. But in barrier membranes, surely by virtue of passive movement. If you are going to look at active transport are supposed to be more meaningful, because you need vitamins in good reserve, and whenever there is basically movement of particles, especially the vitamins, an active absorption would really enable us to have sufficient stores of vitamin even in anticipated deficiency. Okay, so you see there the normal physiologic mechanism is generally active. So it's through the ileum, and it's generally it's efficient for small molecules, so few micrograms it works really well. So the oral doses of cyanocobalamin actually has this association with the gastric intrinsic factor. We are going to look that. So the dietary scopolamine is released from protein complexes by enzymes. So the food what you consume would contain cobalamin, cyanocobalamin in a, I won't say inactive form, it's in a form where it needs to be released by enzymes. So the enzymes in the stomach, in the small intestines, duodenum and jejunum, play a greater role in enhancing the availability of this particular vitamin. So it combines rapidly with the salivary glycoprotein that belongs to a family of cobalamin binding proteins. Okay, it's also called aptocorins. So aptocorins present in your upper gastrointestinal tract, they play a very key role in the absorption process. In the intestines, the aptocarin are digested by pancreatic trypsin, and the cobalamin is transferred to intrinsic factors. So, this is something like in the oral cavity, you have the carin molecules that would selectively bind with vitamin B12, and once they are bound with carins, what we call it like the aptocarin, that is the name we give, and aptocarins are further transported across by peristaltic move in the intestines, and the digestive enzymes, especially trypsin and cobalamin, would basically be the source for intrinsic factor. Okay, so the intrinsic factor, in the presence of these enzymes, modifying it makes it feasible for vitamin B12 to be carried further by intrinsic factor. So, you see the structure, the absorption, how this works. So, you have the food proteins, okay. So, here you have the pepsin of stomach. So, as you consume the food, okay, so you see there aptocarin, the complex of aptocarin with vitamin B12. So, aptocarin comes here and binds with vitamin B12. Okay, so as it goes, so aptocarin acts like a carrier molecule in the first phase. So, dietary enzymes basically in the gastrointestinal tract, and if you look at very closely, they are pepsin and proton. So, it is in an acidic environment. Okay, so they would degrade the extemporaneous kind of components present with vitamin B12, they are removed off, and now vitamin B12 is carried by aptocarin. So, we are going to summarize today's discussion. It speaks about what is the importance of vitamin B12, the complex structure outline I have given you, and we are also looking at different aspects of absorption of vitamin B12, which is very important in terms of the availability of vitamin B12. So, I am going to end with a question. So, enumerate the structural features of vitamin B12, enumerate the stores of vitamin B12 and dietary resources for vitamin B12. And the third question would be, give an outline of vitamin B12 absorption. I think you need to revise these topics, and we will continue further in the coming sessions. Thank you.